We'll look at one more basic mathematical structure in this chapter, matrices. Plural matrices, singular matrix. So a matrix is a rectangle of numbers like this one. So here we have 6 integers, but they could be any kinds of numbers. All right, so this matrix has two rows. So the first row, second row, and 3 columns. So it's called a 2 by 3 matrix. So the first number is the number of rows, the second number, the number of columns. Also written like this, so 2 by 3. Yeah, so just remember it's always rows coming first. And these matrices, they're very useful, lots of applications. Classic, where they came from was solving systems of linear equations, but they're also good for storing and manipulating information. We don't really use them in this course, but they do show up a lot in csi30, so Discrete Math 2. But so we're seeing them now. They're just an important mathematical structure. We know regular numbers can be added, subtracted, multiplied, and divided. And the same is true for matrices. All right, so there's a kind of a matrix arithmetic we'll look at. But before we get to that, let's get into the notation a bit more. So another example, we have this bigger matrix. You can see it has 4 rows and 3 columns, so it's a 4 by 3 matrix. Okay, so altogether it has 12 entries, 12 numbers in the rectangle. There's a 5.2 here. So these could be, again, any kinds of numbers, decimals. And you can give the location of any number. So this 6 here, it's in the second row and the third column. All right, this 0 here, it's in the 4th row and first column. Again, we list the row first, then the column second. So here's the general notation. So let capital A be a m by n matrix. Again, m rows and n columns. We can label its entries like this. So little a and then ij in the subscripts. So a subscript ij, or just a sub ij, you could say. And this means the number in the ith row and the jth column. So here, the number in the in row 1 and column 1, that's the top left, that's A sub 1, 1. Row 1, column 2, that's A sub 1, 2. Yeah, this guy has n columns, so in the top right we have A sub 1n. Okay, first column, first row, nth column. Alright, so yeah, it's a bit complicated, but again, just remember rows first, column second. So A sub 2, 1 is in row 2, column 1. And this guy's in the ith row, jth column. M rows, so bottom left is A sub mi, and bottom right is A sub mn. So that's the way to label the entries, label the numbers inside the rectangle, inside the matrix. And this is the shorthand, so if you could use different letters inside. We're using little a here, but this tells us we're using little a sub ij to label the entries of capital A. For example, for this matrix B, with these numbers, give the numbers B sub 3, 2 and B sub 1, 3. Right now we're using little b's to label the entries instead of a's. Also give the second row as a 1 by 3 matrix. So what is B3, comma 2? Well, we need to look in the third row and the second column. Alright, so third row, second column, yeah, that's that 8. First row, third column, that's this 4. And the second row, yep, I'm just kind of pulling out that second row, writing it as a 1 by 3 matrix, looks like this. Okay, so that's how we can break down matrices. Yeah, this matrix B is a 3 by 3 matrix, so that's an example of a square matrix. Same number of rows as columns. Yeah, this first example, this is not square, this is 4 rows and 3 columns. Definition, a new word. So the transpose of a matrix is found by switching the rows and the columns. Okay, so the first row of a matrix becomes the first column of the transpose, and so on. And we have this notation. Yeah, it looks like a power, but it's for a matrix, A with a T here means you want the transpose matrix. And so if A is an m by n matrix, with entries A sub ij. Well, then what does the transpose look like? Well, you're switching rows and columns, so that's going to be an n by m matrix bij, where bij is equal to a, or b sub ij is equal to a sub ji. So the indices, these numbers get switched. Alright, that sounds complicated, but yeah, we're just switching rows and columns. And so if you want the transpose of this B, well, this first row 0, 1, 4, turns into the first column for the transpose, so 0, 1, 4. So that first row turns into the first column. The second row was 3, 2, 0. That turns into the second column. All right, so the transpose, just the rows of the original turn into the columns of the transpose, and vice versa, so that the columns of the original turn into the rows of the transpose. Matrix operations. So how do you add and subtract two matrices? Well, first they have to be of the same size. Okay, so both m by n matrices, so the same number of rows and columns. And all you do is you just operate on the corresponding entries. So it's the simplest thing you can do. Okay, so A and B have the same size. They're both 2 by 3. So for A plus B, you're just adding the corresponding entries together. So that at the two top lefts, you get 6. So that's the top left entry in the answer, because the result is a matrix of the same size. Or if you wanted A minus B, then that would just be 1 minus 5. How about this 4? Well, that matches the 2. So when we're adding, we'll get 4 plus 2, that's 6. And subtracting 4 minus 2, that's 2. Alright, so adding and subtracting is easy. It only works if the matrices have the same size, and then just operate with the corresponding entries. Alright, you could imagine multiplying two matrices the same way, so just multiply the corresponding entries. But it turns out there's a different way to multiply matrices that's a lot more useful. Alright, so how do you multiply two matrices? Well, it works like this. Yeah, you want rows, you want to multiply rows from the first matrix by columns from the second matrix. How do you multiply a row by a column? Okay, well now you are looking at the corresponding numbers. So the first number in the row here is 3. The first number in the column is 1. So they get multiplied. 3 times 1. And we want to add 2 times 4 plus 0 times -2, that's 0. Alright, so we get a number out of this, 11. Alright, so just remember this again, you want rows times columns, and yeah, so for this to work, that the number of elements in the row of the first matrix has to equal the number of number of entries in the column of the second matrix. In other words, yeah, so here they're both of length 3, so this wouldn't work if this column had an extra number here. Alright, so that's multiplying a row by a column, and when you're multiplying matrices, you're going to have more than one row, more than one column. Okay, so to multiply this 2 by 3 matrix by this 3 by 2 matrix, we get this matrix. Alright, so the first row here gets multiplied by the first column here. Yeah, we did that already. We got 11. Okay, so first row times first column gives the number in the first row and first column of the answer. How about the second row times the first column? So that's going to give the number in the second row and first column of the answer. So how did we get -17? Well, that's 1 times 1 is 1 plus -2 times 4. 1 plus -8 is -7 plus 5 times -2, that's -10. So -7 plus -10 is -17. Alright, so we just did the same procedure. 1 times 1 plus -2 times 4 plus 5 times -2 gives this number. Then first row times second column to give this number. And second row times second column to give this number. Is that 13, right? So it's 1 times 0 plus -2 times 1 plus 5 times 3. Yeah, that's 13. Alright, so you're always multiplying rows by columns. Rows on the left, columns on the right. And multiplying row I by column j gives the ijth entry, gives the number in row I, column j of the answer. Alright, I hope that made sense. Yeah, it takes a little getting used to. And what about the sizes? Yeah, so we multiplied a 2 by 3 matrix by a 3 by 2 matrix. Like I was saying before, yeah, these 3's have to be the same. So we have 3 numbers here times 3 numbers here. So these numbers have to be the same. Okay, so the number of columns in the first matrix has to match the number of rows in the second matrix. And then the answer So when you multiply these two matrices, you get a 2 by 2 matrix. Okay, so 2 rows and 2 columns. All right, so you could multiply a 4 by 7 matrix by a 7 by 6 matrix. It would be a lot of work, but you could do it, and you'd get, so the result would be a 4 by 6 matrix. All right, so that's how the matrix multiplication works. Okay, another example. This matrix M is this rectangle, this array of numbers, matrix N, 2 by 2. Compute Mn, so that if you don't see any operation, that means matrix multiplication. Yeah, this is 3 by 2, this is 2 by 2, so that those 2's match, so the answer will be a 3 by 2. So it's this row times this column first, so 1 times 2 plus 0 times 4. That's 2, so 2 is in the top left of the answer. All right, and then 5 more numbers. Yeah, that's a nice way to set this up so you can keep track of what goes where. So if you write the first matrix as usual, but for the second matrix, instead of writing it here, move it up here. Now the answer is going to go here. And you're kind of lining up so you can see that it's going to be this row times this column to give the number that goes here. So 1 times 2 plus 0 times 4. How do we get this number? Yeah, it's 2 times 2 plus 4 times 4. So that goes here, that's the 20. How do we get this number? It's 3 times 1 plus 5 times 0. Alright, so that's the 3. Yeah, so this is a good way to do it. And you can also see the size of the answer. Yeah, it goes here. It's going to be a 3 by 2 matrix. Yeah, in example 5, we multiplied m by n, but we couldn't multiply n by m since the sizes don't match. Yeah, 2 by 2 matrix times a 3 by 2 matrix. Yeah, we have a 2 and a 3 in the middle. That doesn't work. But if you have 2 square matrices, then you can multiply them in either order, so AB and BA. And we're used to multiplying numbers. 3 times 4 is 12. That's the same as 4 times 3. But for matrices, yeah, you don't necessarily get the same answer if you switch the order. There's an example in the book. Alright, so again, adding and subtracting matrices, multiplying. And yeah, if you want the general formula for matrix multiplication, but yeah, just it's rows times columns. Yeah, this example 4. So we have the square matrix A, 1, 1, 2, 1. Square matrix B of the same size, 2, 1, 1, 1. So if you put A first, so A times B, well, the first row times the first column, that's 1 times 2 plus 1 times 1, yeah, that's definitely 3. But if you do B times A, so the rows of B times the columns of A, then the first row of B is, it's going to be 2 times 1 plus 1 times 2. Yeah, we get 4. So even just checking the top left entry, we're getting different numbers. And yeah, nothing special about these two matrices. Yeah, if you multiply two square matrices in different orders, yeah, you usually get different answers. So matrices, yeah, they do, when you're multiplying them, they definitely behave differently than just multiplying numbers. But you can think of squaring. Yeah, if you have a square matrix, you can multiply it by itself. So that's called a squared, and multiply another a in there, you get a cubed. Okay, so powers of square matrices, you get matrices of the same size. And so yeah, you can take powers of matrices, square matrices, like this. So a special type of matrix is one that just contains the numbers 0 or 1. So those are called 0-1 matrices. No other numbers are allowed inside, just zeros and ones. Probably the most important 0-1 matrix is the identity matrix, with notation I subscript n. So what is that? Yeah, it's a square matrix, size n by n, and all the entries are 0, except it has 1s on the main diagonal. So the main diagonal, that's the diagonal going from the top left to the bottom right. So the entries on that diagonal are 1, and everything else is 0. Yeah, this is I sub 3, the 3 by 3 identity matrix. I sub 5 looks like this. 5 by 5, the same idea. Okay, yeah, two things we can say about this matrix. The first is it's equal to its transpose. So if you can see if you make this first row into a column, the second row, third row, you see you get the same matrix. Any matrix that's equal to its transpose is called symmetric. Alright, so I sub n, the identity matrices are always symmetric. They're equal to their transpose. But a more important property, if M is any n by n matrix, so it can have any numbers, if you multiply the identity matrix by M on the left or on the right, you just get the same matrix coming back. Okay, so this pattern of zeros and ones, for matrix multiplication, it doesn't do anything. You just get the same matrix coming back. So that's why it's called an identity. It's like a 1. It behaves like 1 when you're multiplying numbers. Alright, so that's a well-known matrix, the identity matrix. And it's a 0-1 matrix, just has zeros and ones. Now, of course, back in chapter 1, back in the first section, we can think of zeros and ones as bits, where 0 means false and 1 means true. Don't forget our logical operations. So we have and or. Okay, so we have these operations. We can combine bits. So 1 and 1 means true and true. So that's true, which we can convert back to a 1. Okay, so 1 and 1 equals 1. 0 or 1 means false or true. That's true. So that also equals 1. And one like this, so 1 and 0 is equal to 0. Alright, so you remember those bitwise operations, or and. Yeah, we're not using the exclusive or here. Okay, so this gives us another way to combine matrices that just contain zeros and ones. So if you take two matrices, again, they have to be of the same size, just like when we were adding and subtracting. But this time, instead of adding and subtracting, we're using, well, here we're using and. Okay, so corresponding entries get anded together here. That's called the meet of the two matrices. The join of two matrices, 2, 0, 1 matrices, uses the OR operation. Yes, all we're doing is, instead of using adding and subtracting, we're using and OR operations on corresponding entries. Okay, so there's the identity again, powers. Yeah, just like the 0th power of a number is 1, the 0th power of a matrix is the identity matrix. Here's another example of a transpose. And so the transpose of this 2 by 3 matrix is this 3 by 2 matrix. So this first row ends up here. And the second row of the original ends up as the second column of the transpose. Symmetric matrices, 0, 1 matrices. Yeah, if you want a formula, so if you're ANDing 2 bits together, you get a 1 if the bits are both 1, otherwise it's 0. If you're ORing 2 bits together, it's 1 if either or both are 1, and it's 0 if they're both 0. And we have the join and the meet. So an example of that, yeah, so these 2 matrices have the same size. They're both 2 by 3, just with 0s and 1s. So the join, A join B, is just or the corresponding bits together, so it's going to be 1 or 0, giving the top left entry of the answer. Yeah, 1 or 0 is 1. And then just the other corresponding entries out of the last one, 0 or 0 equals 0, so one of the entries of the answer is 0. And for the meet, it's the same thing. Yeah, the join is OR, the meet is AND. Just use the AND operation. And we have one last operation, is the Boolean product. So this is more like matrix multiplication. The Boolean product is used in, we'll see it in chapter 9. That's covered in Discrete Math 2. Just to see how it works here, so let A and B be 2, 0, 1 matrices. Let's say A is an M by K matrix, B is a K by N matrix. So we need the number of columns here to match the number of rows here, just like in matrix multiplication. Then the Boolean product of these 2, 0, 1 matrices, it has this special notation. It's an M by N matrix, and you compute it just like the usual multiplication of matrices, except that each multiplication is replaced with an and each addition is replaced with an OR. Let's see an example. So here, this is A, this is B. Find the Boolean product, A, B, and the Boolean product, A, A. All right, so for AB, yeah, we're still multiplying rows by columns. If it was just matrix multiplication, it would be 1 times 0 plus 1 times 1. But now instead of that times, we have 1 and 0. And instead of plus, we have or 1 and 1. All right, so for matrix multiplication, this would be a multiplication. This would be a multiplication. This would be an and, a plus addition. But for the Boolean product, for this logical version of multiplication, we have ands and ors. Okay, but still the same deal, rows by columns. So 1 and 0, that's 0. 1 and 1 is 1. So we're doing these parts first, then the or. So 1 or 1 is 1. All right, so yeah, it's quite a lot of work. But we're getting this 2 by 2, 0, 1 matrix is the answer. Yeah, just one more example. So here we're getting the Boolean product of A with itself. Okay, so just switching B for A. And you can check we get these combinations. Yeah, so or is always gives you 1, except in the case where you have 0 or 0. So that's a 0. Everything else here is 1. All right, so that was a look at matrices. Again, a basic mathematical structure that we won't be using so much in this course, but yeah, you will use it a lot. See it a lot in the csi30. And if you take Math 42 linear algebra, then that's all matrices.